Welcome to Introduction to Quantum Field Theory, Lecture 10. In this lecture, I will be talking about how to regularize divergences that appear frequently in quantum field theory. A good reference for this particular lecture is the textbook by Leine and Vuorinen, Chapter 2. First, recall from Lecture 9 that we found a result for the partition function for a free single scalar field in quantum field theory that was given by this expression here, where D denotes the number of space dimensions and EK is just a shorthand notation for the square root of k squared plus m squared. While there's nothing wrong with the partition function itself, for the purpose of the current lecture, it is useful to consider a physically more intuitive observable, such as the pressure P as a function of temperature. For any partition function Z, there's a basic thermodynamic relation that gives the pressure as T over the volume V times the logarithm of this partition function. If we apply this thermodynamic relation to the partition function that we calculated in quantum field theory, we find the pressure to be given by this expression here that's shown in equation 10.3. If you recall that this EK just stands for the square root of k squared plus m squared, the integrand here becomes larger and larger as k increases, and that means that this integral here is divergent for any value of the temperature T. In particular, the divergence is also there if we send T to 0, in which case the second term here just vanishes, and we get that the zero temperature pressure P of 0 is just given by the integral in d dimensions of EK. This is sort of explicit if we plug in the form of EK that shows that this integrand here behaves proportional to K for large wave number K. It is actually convenient to study a slightly more general function than the pressure for further studies. And instead of the zero temperature pressure, I want to consider this function phi here that depends on the mass m that appears in the integrand, the number of space dimensions d that appear in the integration measure, and the exponent a that appears as the exponent of this expression EK here. It is easy to express the zero temperature pressure of the free scalar field theory that we were just discussing by plugging in D is 3 and the exponent of -1/2. And we find the pressure of zero temperature to be given as -1/2 phi evaluated at these arguments. If we look at the integrand of this expression for phi, we see that it only depends on the absolute value of k vector. That means that we can do the angular integral and we find that the function phi is proportional to the integration over the absolute value of k times the solid angle in d spatial dimensions, which I denote as omega d. And omega d is given by this expression here. This is just a fancy expression for the solid angle that in 3 spatial dimensions evaluates to the familiar 4 pi, in 2 dimensions is 2 pi, and so on. Note that the integrand that we have left here is well behaved for any k as long as m is non-vanishing, which we assume in the following. If we do that, then if we indeed recall that eventually we want to evaluate this function here for an exponent that is, for instance, -1/2, the only divergence that appears in phi arises in the limit of k to infinity. Borrowing from the nomenclature of light, which, since we call the light above the visible spectrum ultraviolet, we will call this high wave number divergence that appears in the integral an ultraviolet divergence or UV divergence. And later on, we will also encounter divergences that appear in the zero wave number limit, which by analogy, we will call infrared or IR divergences. Let us first study the so-called superficial degree of divergence of this function phi. Since the divergence is in the ultraviolet, we can concentrate on the high momentum mode behavior of the integrand. So that means that all other mass scales can be neglected in the integrand. Then we cut off the momentum integral at some high scale lambda, and since we can neglect all other mass scales, so we sort of set m to 0 in the integrand, we get an integral that is evaluated at the momentum cutoff lambda that is easy to evaluate. So we find that this integral here evaluates to lambda to the d minus 2a divided by d minus 2a. In the case of the pressure, where d is 3 and this exponent a is minus 1/2, this gives that the zero temperature pressure is proportional to the momentum cutoff lambda to the 4th power. So as the momentum cutoff lambda is sent to infinity, we find that the pressure diverges with degree 4 from this expression, 10.8. For the case at hand, it's actually possible to evaluate this expression analytically. So if we evaluate this expression here for d is 3 and a is minus 1/2, we find the exact result for the zero temperature pressure in the presence of a momentum cutoff lambda, and it's given by an expression that contains this divergence of degree 4, but there's also a subleading divergence of degree 2 and a sub-subleading divergence that's just logarithmic in the momentum cutoff lambda. So now we have regulated the divergence using a finite momentum cutoff lambda. However, that's not the only possible way to regulate a divergence. In the following, we would be talking about a different regularization scheme, which is called dimensional regularization. So instead of introducing an ultraviolet cutoff lambda, we find that the integral that is written down for the function phi can actually be solved exactly for arbitrary value of d and arbitrary value of a. It is given in terms of an expression that involves the gamma function that is evaluated at these various arguments. And we can further simplify this expression by plugging in the known result for the solid angle in d dimension and just some basic forms that the gamma function have to fulfill. So we are left with the expression shown in the second line of equation 10.10. If we again plug in the values that are of interest for the zero temperature pressure, so d is 3 and a is minus 1/2, this gamma function here is evaluated at minus 1/2 minus 3/2, that's gamma of minus 2, and gamma of minus 2 is just infinity. So the divergence of the pressure is just given as a divergence of the gamma function evaluated at negative integer number. The trick that we want to use now is that we work in almost, but not exactly, 3 dimensions. So we put d not equal to 3, but we put it equal to 3 minus a little bit, and we quantified a little bit as epsilon, where epsilon here in the end should be taken to 0. If you plug in the spatial dimensions to be 3 minus 2 epsilon, the result for the function phi takes the following form here. And we find that this result here is finite as long as epsilon is not 0 and doesn't get larger than 1. Using the property of the gamma function that x times gamma of x is gamma of 1 plus x, we can rewrite this expression for gamma of minus 2 plus epsilon so to make the divergence epsilon to 0 explicit. So we find that gamma of minus 2 plus epsilon is gamma of 1 plus epsilon divided by minus 2 plus epsilon minus 1 plus epsilon divided by epsilon. And you can see that this expression here is indeed still divergent as epsilon goes to 0. So once we have made the divergence of the dimensionally regularized integral explicit, we can expand all components of this function phi as a power series for small epsilon. So for instance, we have the expression 4 pi to the power of minus 3/2 plus epsilon appearing. And we can just expand this for small epsilon, where we get a leading order term, 4 pi to the minus 3/2 times the expansion of 4 pi to the epsilon, which just gives us epsilon logarithm of 4 pi. A similar expansion also applies for the expression m squared to the power of 2 minus epsilon, which we write as m to the 4 times m squared to the minus epsilon, and then expand the second term here for small epsilon, so we get a logarithm of m squared. Finally, we have the gamma function, which we rewrote in this particular form to make the divergence epsilon to 0 explicit, and then we expand the rest of the argument in terms of a power series of epsilon, and we find the following result here that then involves a particular number, namely Euler's constant, that comes from the expansion of the gamma function. Once we have this, we plug in all the pieces into the expression for the 0 temperature pressure, and we will find the following result here, where the 0 temperature pressure is given a term here that involves 1 over epsilon, that's the divergent part, plus some finite pieces and pieces that go as order epsilon. So these will become very small as we take epsilon to 0. Again, the pressure still diverges when we take epsilon to 0, as was the case with the cutoff regularization that we were discussing earlier. There's only one weird thing that appears in this expression, which is that we have a logarithm of m squared, where m is a mass scale. So we have the logarithm of a dimensional quantity. That's something that we shouldn't have. All the arguments of the log should be dimensionless. And we can trace this back to the expansion of this mass squared to the power of 2 minus epsilon that appeared in the previous slide. Now, the quantity that we have, this massive or mass scale object to a non-integer power, that can be traced from the fact that we have taken the integral measure to be evaluated in non-integer spatial dimension, so 3 minus 2 epsilon. To avoid something like this, we basically have to slightly modify our function phi when we take d to be a non-integer value of space dimensions. Basically, what we want is we want the expression for phi to always have the same mass dimension, no matter what epsilon is. So no matter in which fractional or non-integer spatial dimension we work, we always want this to have integer mass dimension. And it's easy to repair this by just multiplying the expression that we use in non-integer space dimensions by a function or a scale mu to the power 2 epsilon, such that this, together with the minus 2 epsilon here, makes up just an integer value for the mass dimension of the overall function phi. The scale mu here is completely arbitrary. We just put it in there such that we don't have a logarithm of a mass scale. The only requirement is that indeed this mu here also has mass dimension 1, such that it can properly sort of cancel the mass dimension that was appearing in the logarithm earlier. So with this mu in place here, we have an expression for phi that ensures that the pressure has integer mass dimension, even if epsilon is non-zero. And we give this mu here a name. We call it the renormalization scale parameter. Again, it's arbitrary, but we have to give it some name. And once we sort of use this modified expression for the function phi, we find a similarly modified expression for the pressure that then looks exactly the same as before, except that instead of having logarithm of m squared, we have logarithm of mu squared over m squared with the corresponding change in the sign here. This expression here is perfectly fine, but it turns out that it has been found that it's useful to still modify the scheme a little bit further by lumping together the expressions 4 pi and this Euler gamma constant and define a modified scale parameter mu bar that is just given in terms of mu bar squared is just given in terms of mu squared times 4 pi e to the minus gamma. So if you plug this in here, we find that it just cancels these two terms here and it gives us a slightly nicer expression for the zero temperature pressure when we express everything in terms of this modified parameter m. So ms bar really stands for minimal subtraction modified scheme. So that's the name of this subtraction scheme, and it is by now a standard in quantum field theory calculations. So if you open up your textbook on particle data, essentially all the quantities are expressed in the so-called ms bar scheme. And that concludes the present lecture.